All right. So from the Python library called PEFT, parameter efficient fine tuning, you can actually import a few useful um, functions: LoRa config, get perf model, task type. So this LoRa config is a function that basically generates a configuration object that captures information about the rank. This rank could be different options, but typically people use 4, 16, 32, these powerful two numbers. In the previous example that we showed just now, that was the rank is 4 because that's the number of columns in A and the number of rows in B. So this R is the rank. LoRa alpha is a parameter that can be used to basically scale the parameters. Um, and that's a parameter discussed in the paper. You could use um, also for the target modules. This is a option you can use to selectively apply to different layers in the pre-trained model. Because for pre-trained model, you have, you know, however number of transformer blocks, and within transformer blocks, you have different, self-attention layers, and you could choose to use which layer to do this LoRa retraining. So that gives you a lot of options to select individual layers or exclude some of the layers. Um, the other parameter you often use is task type causal LM because they will use only mostly use this to on these pre-trained large language models. And then once you have this LoRa config parameter set, you will set up this training arguments, which will be passed into a trainer function to actually start the training process. Um, I forgot to mention that you can use this getPerf model to load the original pre-trained model with this LoRa configuration. So this PFT model will be the one that you pass into the trainer function to perform the training. Um, yeah, also the token, the training data size. So you can have a lot of options to how define how you want to use this PFT model. Um, you can save the model after the fine tuning. Um, for example, in this case, we could load the base model. That's the from Facebook OPT 350 million. You can then use the LoRa config that you did earlier to load to establish the perf model for training. So you basically use the base model with LoRa config, and then you have a LoRa model. You can actually check the information about this LoRa model by print the trainable parameters. Um, so for this case, we're talking about all the parameters is 300 32 million, and for trainable it's about 1 million, 1.5 million. So once you finish the training, you can save the pre-trained model, use a different name, or you can even excuse me, you can even push the newly fine-tuned model to your Hugging Face place hub under your account. And later, you can just load this pre-trained model directly by calling this perf model from pre-trained. Okay, so when you have a model that you pre-trained using LoRa, so you basically have a much smaller set of parameters that's basically defined by the matrix B and A, and we call this set of LoRa matrices as the LoRa adapter. So you'll find this terminology used in different places. So LoRa adapter is really uh, the um, the matrices that you train in the fine-tuning process using LoRa method. And these adapters are for a specific task. Of course, depending on what kind of training data set you have, you probably name it differently, but that's this fine-tuned for your specific task or domain. What you could do is you could um, you know ha create create a new integrated model with by adding these matrices on top of the original model. So that's what we call the merge. So you can merge these LoRa adapters for a specific task to the base pre-trained model. Well, why do we do this? Well, next time when you load it, you don't have to load it separately or do the addition of these parameters separately. And this merge and unload function will basically create a new model that you can use right away. So there'll be no added latency when you want to use this fine-tuned model on top of the base model. A different alternative that you can have is if you have a few tasks you may be running. So you may do summarization, you may do some translation for different tasks or different tenants. Um, you could maintain separate LoRa adapters. The benefit is that because these LoRa adapters depends on the original pre-trained model. So when you have multiple adapters, they can use one copy of the full-size pre-trained model. So you don't have to have other storage spaces allocated to store the same full-size model multiple times. So in this case is that we can use this uh, uh, separate LoRa adapters, and when you want to use them, you just call this perf model dot from pre-train, give the original model's name or ID, and also the path to your adapter. So in this case, tenant one LoRa adapter. So that's where you store your LoRa adapter for the first task. And then for the other task, you can use a different path, but this original model will be the same that is shared across all the different tenants. Okay, just to compare the performance between fine-tuned model, full fine-tuned versus LoRa fine-tuned. Um, Here's an example using the dialog summary data set and using the Roche metrics. It's for base model, so that's before fine-tune. Um, and second column is the full fine-tune. And the LoRa fine-tune is compared with the full fine-tune. So we can see that for um, Roche 1, so there's increase of Roche 1 score from 0.23 to 0.42. By the way, Roche scores are between 0 and 1, 1 being the best. So that means the output matches the reference summary, 100%. Basically, that's like ideal situation. On the other hand, 0 means that the output summary doesn't really make sense. So the higher the better. Um, so here for Roche one, after full fine tuning, we increase about 80% or more even. And but compared to the full fine tuning, LoRa fine tuning, does have a little bit performance hit, so 0.4 versus 0.42. So about 3% of decrease. So all the Roche metrics you can see the same trend. All right, let's let's continue. All right, so that was about LoRa. Then quite related is QLoRa. So before we explain QLoRa, we want to explain about the memory utilization in the training process. This training meaning including pre-training and fine-tuning. So essentially, when you have a model that consists of billions of trainable parameters, uh, you need to be aware that in the training process, you don't just store these billions of trainable parameters. You also need to store additional information that are necessary in this training process. So what we're talking about here is that you will store the model parameters, the matrix weights, of course. You also need to store information about the atom optimizer, which essentially, keep the derivatives in the back propagation process. And also you need to store the gradients and also the activations. So all these intermediate computations and their states have to be stored as well, in addition to the model parameters. So a rough calculation uh, that shows that for each parameter, you need more uh, bytes than the original parameter itself. So essentially, you're talking about additional 20 bytes that needed to store, in addition to store these original parameter. So that's a lot. Um, to give an example, for this 1 billion parameters model, we're talking about 4 gigabytes of space. And then this size depends on the size of these parameters could be reduced. If we quantize, if we apply quantization, which is the topic we'll talk about not next week, but probably the week after, it's essentially to reduce the size of these parameters, but try to maintain the precision of them, which is hard. That's why there are different options of doing this quantization. But what we want to show here is that the GPU memory is still a scarce resource, which will require us to reduce the number of bits that we use to store every parameter or intermediate states. So that's why we use a method called QLoRa. Q stands for quantization. So the basic idea is to use a instead of use 32 byte, we use 16, 8, or even smaller. Uh, sorry, 32-bit parameter. We use uh, the 16, 8 bit or even 4-bit to store information. For that, we'll rely on a library called bits and bytes, which is a good library, Python library that implements the different quantization methods. Um, so what you see here on this code is a in addition to this LoRa config, we have to config a bits and bytes configuration object that declares how we're going to do the quantization, how many number of bits we will use, and what will be the quantization type that we choose to use. And we're going to pass that into the in the in the when we load the model, we will apply this quantization configuration so that this model is quantized. Um, I'll revisit this slide after we talk about the quantization method in about 2 weeks.